My name is Carmel Rabinovitz, and I will be presenting our work on unsupervised feature learning for manipulation with contrastive domain randomization. This work was done in collaboration with Nico Gruppen for Cornell University and my supervisor Aviv Tamar from the Technion Israel. Learning plannable representation from visual inputs is a necessity for many different robotic tasks. We wish to learn good features that capture important properties of a scene, which may include deformable objects such as a rope, multiple objects, or objects with non-trivial geometries. We then wish to perform planning in the learned latent space. Good features for manipulation capture physical properties of a scene, such as positions, orientations, and relation between objects. In this work, we wish to learn such features with no supervision from simulated random robot interactions and transfer to a real robot that executes actions in the real world. Domain randomization is commonly used to transfer from sim to real. This way, we do not require to define a reward function, and therefore the learned features are task agnostic. Recently, self-supervised contrastive learning methods, such as CPC and CFM, have shown promising results in learning such representations. On the left, images of a rope from prior work with a small sim-to-real gap. On the right, a more realistic and substantial sim-to-real gap that we explore in this work. Top row consists of simulated images and real-world images on the bottom. Note the visual properties that differ from sim to real, such as colors, textures, light, domain differences such as exact frame boundaries, and unseen during training distractors. We wish to learn representations that overcome the sim to real gap, ignore irrelevant visual differences, and encode only relevant physical properties, so we could deploy our planning algorithm in the real world. Prior methods, like CFM, use domain randomization to transfer from sim to real. In this work, we show and provide an explanation on why naive application of domain randomization to contrastive learning does not promote domain invariance. We propose a new algorithm called Contrastive Domain Randomization, or CDR, and prove that under mild assumption, CDR produces domain invariant features. We also show that we can use simulated goal while performing with a real robot, which is useful for goal condition algorithm. We first explain how contrastive learning was used to learn plannable representations as done in prior work. Given a trajectory of observation, O at time t, we wish to train an encoder, G, a neural network, that extracts feature by maximizing the mutual information between the latent representation Z at time t and Z at time t plus 1. To do so, we jointly train a forward model, F, that predicts the future in latent space and use the prediction to classify and distinguish between the positive future, Z at time t plus 1, and random negative samples that are drawn from different times or episodes. We define a similarity function between features, H, such as cosine distance, and use cross entropy as the objecting function for the classification. Basically, the loss function tries to classify if our predicted future latent representation is more similar to the true future latent rather than random latent representations. Maximizing the mutual information encourages the neural net to encode physical properties that are useful for predicting the future. Now, assume that the observations are generated from a combination of the state properties xt we are interested at, and the domain visual properties E we are interested to ignore. Maximizing the mutual information between ZT and ZT plus 1 results in learning features that are related to both the physical properties and the domain properties. Since the contrastive objective is based on discriminating between samples, applying domain randomization may encourage the neural network to exploit spurious connection of the domain properties instead of the state properties, as they can be a good distinguisher between positive and negative samples, such as textures. This may lead to domain-dependent representation and thus poor sim-to-real generalization, as we will show next. We generate data using domain randomization and train an encoder as done as prior work. We then sample random images from our data, extract latent feature using the trained encoder, and retrieve the top 5 nearest neighbors in latent space from a set of examples unseen during training. As you can see, the rope configuration is captured in most cases. The top 4 out of 5 retrieved images come from the same domain, which implies that the learned representation are domain dependent. This phenomena is repeated in multiple cases. To learn the main invariant feature, we propose a simple modification in the contrastive loss. The key point of this work is that we can control the domain properties in simulation. We sample a sequence of random actions, as before, but generate two sets of observation, O and O', with the same state, x, but different random domains. Note that the two sets of observations on the right has the exact same probe configuration and locations, but with different textures and light. We then replace the positive observation at time t plus 1 with O', taken from the different domain. Now, since zt and z' at time t plus 1 does not share any domain information, maximizing their mutual information results in learning domain invariant features that are related to the physical state x alone. We use this simple modification in the contrastive loss to form the CDR objective function. This objective function cannot use domain properties to distinguish between positive and negative samples. In the paper, we proved that under mild assumptions, this objective guarantees domain invariance. We experiment with multiple environments. For the uncontrolled environment, a random force is applied to a rigid object in a blocked frame, making it collide with the frame and the second object over time. For the control environment, a cube agent interacts with two complex rigid objects by pushing them in a random direction at each time step. We also experiment with a complex deformable rope. In each time step, the rope is being pushed in a random direction by a robotic arm. We design our evaluation carefully to answer the following questions. Did we learn features that are captured with the physical properties of a scene? Are they domain invariant and we can transfer from simulation to a real robot? Are they useful for planning with a real robotic arm? And can we plan in real domain from simulated goals? As before, for each reference image, we retrieve the top 5 nearest neighbors in latent space, but this time using CDR trained encoder. Notice that the latent nearest neighbors we retrieve come from diverse domains and are much more informative of the true underlying structure of the rope, which implies that the features are more domain invariant. To test domain invariance, we generate couples of observations with a different domain but with the exact same state x. We use unseen during training textures. We then measure the cosine similarity between their latent representations and show that our method is much more agnostic to the domain. For the rope experiment, for example, CDR learned to almost completely ignore the domain, 0.97, where 1 is the maximum similarity score. Some of our experiments were done during the COVID-19 restrictions, so we collected real-world images from home to test sim-to-real generalization using information retrieval as metric. To test if we capture physical properties, we retrieve the nearest neighbor in latent space from a simulated dataset and compare the intersection over union between the reference and the retrieved image. Higher IOU values indicate our features capture correctly position and orientation, and able to retrieve observation with similar physical properties. We also provide qualitative results using real images and reference images in the left column. Note that even with the substantial sim-to-real gap, our method on the middle column retrieves simulated observation that capture more accurately the relation and position between the objects. Finally, to evaluate if our representations are useful for planning, we use a simple one-step MPC. Given the current and goal observations, in this case just a simple cube, we first encode them to get their corresponding latent representations. We then sample n random actions and run them through our forward model, which outputs predicted z at time t plus 1 for each action. We measure the distance using the similarity function we define h and choose the action that corresponds to the minimal distance. We then execute the action and get a new current observation, and so on. We use a Franca Panda robotic arm to push a cube to a goal position. Here are examples of trajectory planning in real time. On the bottom, the observation fed into the encoder as captured using a RealSense camera, positioned to look diagonally down at the scene. We train the encoder and forward model from simulated random interactions of a cube in a plane scene. We randomize over colors, textures, light, cube size, and small perturbation of the camera position. Note that all objects in video number 2 were not seen during training at all. The current and goal observations can come from the same domain or from different domains. This enables the use of simulation to generate goals and is achievable due to the domain invariance representation produced by our method. We test our method using diverse and non-trivial texture, light, and unseen distractors. We start from a plain scenario, which is similar in nature to the simulated training data. We also test when many unseen distractors are scattered, and next, we use simulated image as goal observations. Finally, we test our method using a challenging checkerboard as a distractor with real or simulated goal, and even dealt with partial occlusions. Our method managed to encode useful feature for planning even in these very challenging setups. We use contrastive forward model as baseline and report the Euclidean distance between the final Cartesian position as executed by the robotic arm to goal Cartesian position, showing that our method does indeed work a lot better than the baseline. The top table presents the results in simulation. The bottom table presents sim-to-real results, where training was done in simulation and we perform with real robotic arm. To conclude, we suggest a simple modification that significantly decreases the sim-to-real gap and learns domain invariant representation with no supervision at all. This modification is general and can be plugged in to any contrastive objective. Thank you for listening.